G'day, Michael here. This little video is about the progress with my CoreXY unit. I've got the frame sitting here upside down so as to demonstrate the belt arrangement. But first things first, what was important to me is the whole structure is very lightweight. So this whole assembly would be probably maybe 1500 grams, very, very light. There's almost, well, no weight in it. I'll use a cable tie and just push it around. Well, I think I can do that. Not quite. Okay. So certainly the cable tie is enough to push it left to right, so you can see how little resistance there is there. And most of that's still actually drag from the belt. The other way is, well, the other way is still very little drag, and it certainly is capable of pretty high speed movement without much resistance at all. The camera's not really keeping up very well. Okay. So this is actually much less resistance than the bearings on the Black Widow, which are using the V-slot. So it's been a complete success as far as, you know, low resistance with this bearing arrangement. Now what I'm going to do is put these belts back on. Give me a second. Okay, so the belts are on. I haven't got the belts tensioned yet because I'm still actually printing the tensioner. But actually, line that up. A few parts are not in position yet. Take up some of the slack. Okay. So what is important here, obviously, I'm not sure I can show this very well. Come on, focus. Have to focus here, maybe. There we go. Okay, I'm doing my best to keep the belts and everything, you know, perfectly aligned. This is a temporary pulley. I'm waiting for the real ones to turn up. So I've probably got to wait another week or two for those to turn up. Motor on this side. There's no such thing as a real X motor and a Y motor. They have to be nominated as a motor in the controller, but the result is that to make a move to the left, let's say, this motor, it has to turn, as you can see, actually I'll look down on it. This motor has to turn clockwise, and this motor also has to turn clockwise. So both motors are involved with moving that carriage, the Z-axis carriage, to the left. And conversely, if I'm to move that to the right, we've got the motors turning counterclockwise. So that's very cool. Now, if I was to move the whole assembly, I'm hoping this will work. If I'm to move the whole assembly, you see this motor here is working, and that motor there is also working. So every action that this makes involves two motors. Now, why would you bother with such a complex arrangement? Well, I didn't invent this idea. I'm just going to be using other people's work, basically, thanks to the open source world. We've got the ability to develop and share our development and make things work. This principle is called CoreXY, and the big plus is both motors are used to accelerate the XY axis motions in any direction, you know, that is chosen. So to move the carriage in an X-axis move, you need both X and Y motors running. I shouldn't really call them X and Y because it's confusing. Let's call them motor A and motor B. So motor A and motor B are involved with an X movement, and motor A and motor B are involved with a Y movement. And it's only a diagonal move that would involve one motor. So it's kind of a hybrid between the principles of a Cartesian and a delta. I've got a delta running right now, so we might have a look at that. Okay, so the delta also has no real X, Y or Z motions. There are simply three motors working. That's quite a complex little mess here. Three motors working together to produce whatever the motion is. As a result, the unit can accelerate at a crazy rate. Whereas a Cartesian simply cannot accelerate like this because an X movement costs energy from the X motor only, and no Y or Z movement. As a result, there's a lot of speed that's going out of this, and what I'm doing with the CoreXY is much the same. Now, you can see very badly, the V-slot arrangement involves the bearing sitting at a 45-degree angle. I don't know how well that's going to show up. I hope it shows up better than it looks like it's going to show up. Is that going to work better? Okay. You basically got surfaces running at a 45-degree angle, which creates a lot of friction. And that's what my little plan was out there, to have everything running on a flat surface. The amount of resistance in this frame is quite high. I think there's more resistance just in this Y motion than there is in the whole frame out there. So I'm hopeful that the machine will perform very, very well at high speed and give me good precision. Oh, another delta is just fired up. I started a new shape. Hopefully you can see the crazy acceleration of a delta. Now what I'm hoping is that the CoreXY will do something akin to this acceleration. It probably won't be quite as good as a delta, but it'll be a lot better than the Cartesians. They're actually, I'm still absolutely flabbergasted how fast this thing can move. Alright, now let's have another look at the CoreXY. Okay. Now I've tried my best to integrate parts to do a lot of functions in one go. Now this component here is both a joiner for the two frame components, and it holds the motor. And of course there's a left and a right, one on the far side, one on the near side. And at this end we have a left and right set of idlers. Now they have to operate on two different planes so they can get past each other, because obviously this lower belt has to be in line with the actual carriage, the X-axis carriage, and this one is just to get the belt past the other belt. Okay, so the crossover, here, I haven't got the belt tensioned. The parts that are in the deltas right now being printed are the belt tensioners, so I'll have to wait till tomorrow probably before I can set that up. Anyway, I'm pretty happy with how all this works. There's zero play in everything. There's, everything's behaving itself beautifully. And, well, I hope that's of interest to you. Feel free to like, share, subscribe, ask a question, leave a comment. Bye for now.